Hello everyone, and welcome to the final video in this series to support the self-study assignment analysis of N of 1 trials. In the previous videos we covered some of the basic concepts underpinning Bayesian statistics. We have learned a little bit on how different data types are represented in R, and from there on we started with defining priors, choosing likelihood functions, and combining these to get a posterior distribution. Then we sampled the posterior to interrogate it and get some parameter estimates or maximum a posteriori in Bayesian terms, and confidence intervals or credible intervals or highest probability density intervals in Bayesian terms. The last video we dealt with some actual data and also showed how you can compare different groups without messing up your priors. Now we're going to combine all this and use it to analyze our N of 1 data. So here I have the data set, and I'll just load it and show it to you. So this is a data set of an actual N of 1 trial. It's been published. That's been performed at the Robert University, where people who have a magnesium wasting condition were treated with magnesium gluconate, aspartate, or magnesium lactate. And this is some actual data. So here we have in the first column is the period of treatment, which preparation that they had, which I just recoded. What was their serum magnesium at the start of each period, at the end of each period, and so on and so on. There's also some questionnaire data for the RRD quality of life score, with the physical component score, the mental component score, and some questionnaires about fatigue and muscle soreness. For now we will just focus on what was the urinary magnesium excretion during this trial. Before we analyze the urine magnesium excretion, we're just gonna rescale it or standardize it so that it becomes a normally distributed variable with a mean 0 and a standard deviation of 1. And if we plot the density of this, it should look like a sort of you see that most values are within this -1 to +1 range. Now obviously there's only a very few variables here, or values here, only 9, which means that we'll never see a very nice distribution. And this is something important to note. So we know from our background knowledge that if we were to measure urinary magnesium in the general population, or in students for instance, we would expect to see a normal distribution. So even though we have very few actual data points, we can still say, okay, we know from our knowledge that this is a normal distribution, and that the normal distribution is a very, how do you call it, safe or robust choice in terms of a prior. If you have very little information, a normal distribution is almost always good. So here's our model where we want to determine the urine magnesium excretion, and we say that this excretion has some value for its mean called mu, and some value for its standard deviation called sigma. For the mean, we have a separate mean for every preparation. Every preparation might be magnesium gluconate, magnesium aspartate, or magnesium lactate. We assume that these are that all of these the mean excretion after being treated with all of these preparations is similarly distributed. So we've rescaled it to a standard normal distribution with a mean of 0 and a standard deviation of 1. For the sigma value, we take the exponential distribution, and remember from one of our first videos that the exponential distribution, a standard exponential distribution, ranges from 0 to 5 approximately, which makes sense for the standard deviation for a normal standard standard normal distribution. Again, we use this quadratic approximation like we saw in the last few videos. And we put this model into actual R code. The data we've called D, and the data has been called up here. So we run this model, and we take a look at what happened. So remember, the value number 1 is the gluconate, value number 2 is the aspartate, and value number 3 is the lactate. And we can see that the lowest excretion is when we use the aspartate, and the highest excretion is when we use the lactate, and the gluconate is somewhere in between. Now this is a little bit hard to gauge from numbers alone, so let's just plot this as well. So now we've got the labels, and we've got we've plotted the mean values along with their standard deviations in this plot, and here we can see these numbers represented in the plot. And we can also sample the posterior, because still a plot like this, it gives you a sense, and it gives you a sense of which preparation might result in the lowest excretions, but sampling from the posterior means that we can interrogate it. So we're gonna sample the posterior using the extract samples command, and we're gonna plot these values, add a legend, add some labels. You don't have to understand exactly what's going on here with this R code, but this is just to create these density plots. A separate one for each of the posterior distributions after using a certain preparation. This is to add a legend. This last bit is just to add some axis labels to the x-axis. So now we've got the posterior distributions after our subject has taken these preparations. So in red lactate, in blue aspartate, and in black gluconate. And we can immediately see that the highest excretion is in the lactate group, with an average value of slightly under about I think 3 and a bit, and the average after aspartate, which is low excretion, would be 1.5, 1.8 approximately. So from our scientific point of view, we might want to ask the question, so what is the probability that the magnesium excretion will be lower with aspartate than with lactate? In other words, does aspartate work better than magnesium lactate to reduce magnesium excretion in this magnesium wasting condition? So to do this, we can take the difference between the posterior distributions for lactate and aspartate. So lactate was number 3, and aspartate was number 2 in blue, and we can show this difference. So here you can immediately appreciate that most of the distribution of the difference is below 0. So actually a very large portion of the distribution of this difference between aspartate and lactate is below 0, indicating that in most of the times aspartate will result in a lower magnesium excretion than the lactate. How often? Well, to count that up, we use what we've learned from interrogating the posterior. We take the sum of we count up all the times that the difference is lower than 0, which is close to 9,700, and we divide it by all of the elements. And this gives us the probability. So there's a 97% probability that the aspartate will result in a lower magnesium excretion than lactate. And this is basically our answer. There's a 97% probability that aspartate is better than lactate for this patient. In the rest of the self-study assignment, there will be a few questions where you will be asked to review some of this content, and also to try this on your own with a new model, where instead of looking at the magnesium excretion, which is not that clinically relevant, at least not to the patient, and think about what kind of measures would be relevant to the patient. So there's lots more data in here about, for instance, muscle soreness, fatigue, that you might also be able to analyze, or after having learned how to make a Bayesian model of your own. So we do invite you to try this, and if there is any questions, you can ask them during the interactive lecture about this topic. So thank you for your attention, and I'll see you online.